Hi everyone, welcome to this lecture. So in this lecture, we will learn about the first kind of regularization known as ridge regression or L2 regularization. So ridge regression is useful when data has noise and correlation. Ridge regression using squared penalty on the vector. So what happened in ridge regression? So ridge regression is try to avoid the overfitting, and it is useful if the data has extra noise and the correlation. So this is our equation of a least square. So in order to perform the ridge regression, we have to add the regularization term in that equation. So this regularization term has the square on the weights. So basically it uses squared penalty on the vector W. Since it is using square, that's why it is also known as L2 regularization. So this is the way we apply a ridge regression. So we add the regularization term which has the squared penalty on the weights to our regular least square problem. So in this way, we can set up ridge regression. So ridge regression shrinks all the weights, especially the large weights, and thus try to stop the model from learning the noise and keep the training smooth. So basically, if we see that in the ridge regression, we have the parameter known as lambda. So that lambda controls the adjustment between the first term and the second term, that is between this first term and the second term. So if the weights are very large, in that case, the value of lambda will be very small so that we can keep the balance between both these terms present in the ridge regression. So value of lambda basically controls the amount of the weight. So if they are moved in the opposite direction, so if the weights tends to increase, then lambda tends to decrease in order to keep the balance. Now there are two special cases. So case one is when lambda is approaching 0. So what will be the situation and when lambda will try to approach to 0? So if weights tends to approach infinity, if weights tends to become very large, so in order to keep the balance, the lambda will try to approach to 0 so that the balance between these two terms will remain. So in that situation, the lambda will be approached to 0. So if we put 0 here, then the regularization term will become 0 and we are left with our normal least square solution. So the ridge regression will be equals to the least square regression if the lambda is approaching 0, and it will happen only when weights tends to approach towards infinity. The second situation is when lambda is approaching to the infinity or to a very large value. In that situation, what will happen? So lambda will try to approach infinity only when weights will try to approach 0. So if these weights are 0 or close to 0, so in order to keep the balance, the lambda will try to reach to the infinite value. So in that case, when lambda is approaching infinity, it means weight is 0. So if the weight is 0, so this term will be vanished and this term will also be vanished from this square values, and we are left with only y square. So the ridge regression will always will only equal to y square, which are the target value. So we cannot reduce the target value. It means we do not need a ridge regression. In that case, ridge regression will be 0. So if lambda is trying to approach towards infinity, so that is the situation when ridge regression becomes 0. Let's understand more about the ridge regression, and we will try to solve the problem on a ridge regression. That is, we will use ridge regression in order to find the optimal weights and bias value for the regression model. So that bias and weights will try to avoid the overfitting. So this is the objective function of a ridge regression. We have seen that. So if I expand this term, so in the solution of least square, we see that this term is the dot product of these two terms. Okay, and if we want to open this term, if we want to expand this term as well, so this will be also the dot product of W transpose and W. So if I expand this, it will be like a minus b whole square. So this expansion, so this part of expansion we have already seen when we derive the equation for the least square method. And here is the term. Now, what we can do, we can expand this term as well. So this is the square. So this term is the dot product of xw transpose and xw. Then we can arrange the term. We can apply this transpose both on the w and x. So it will get W transpose, XW, and all the remaining terms are same. Now, the further change is that we can bring W transpose and W close to each other. So we can make it a W square, and we can make also this WT and W as a W square. Now we have arranged the term. Now it's time to differentiate with respect to W, and then we will set it equal to 0. So we learn that the least square problem is a convex problem where we have a global minimum at one point, and in order to find the global minimum, we need to find the slope. The slope will be calculated by taking the first derivative of this loss function with respect to W and set it equal to 0. So if we take the derivative with respect to W, so this term will become 2x transpose y, because W will be cancelled out during the differentiation. So this term will be 2W x transpose x. Here we have arranged, we have put the W away from the 2. So it will be basically 2W x transpose x, and this will become 2 lambda W. So we have to put it equals to 0. So if we put it equals to 0 and move this negative term to the right hand side, we will get this. Now every term has 2. So divide this equation by 2. By dividing this by 2, we will get this equation. Now the last step is that we are looking for the W, that is the optimal set of weights for ridge regression. So we will take W common from both these terms. So if we take W common, we will left with lambda plus x transpose x. So these are the matrices. Since all these are the matrices, therefore I am multiplying the lambda with the identity matrix in order to transform this into a matrix, because we know that lambda may be 0, lambda may be infinity, but it is a singular value, it is a single value, it is not a matrix. So in order to transform this into a matrix so that we can perform addition, I have multiplied this lambda with the identity matrix. Now solving for W means I have to move this whole term to the right hand side. So all these are matrices. If I move this whole term to the right hand side, I will have to calculate the inverse. So we can see that this is the ridge regression. This is the method of finding the optimal value of the weights and bias during a ridge regression. So if we want to confirm our cases which we studied before on this equation, we can also confirm. So if I put lambda equals to 0 here, what will happen? If I put lambda is equals to 0, so this term will be vanished. So I will left with this term. If you remember, this term is a least square term. So this term will be a least square method. So our ridge regression will be equals to the least square method if lambda is 0. On the other hand, if I put lambda equals to infinite, what will happen? So if lambda is infinite, then infinity plus any other terms will also be equals to infinity. And here we are taking the inverse. So if we take the inverse of infinite, we will get 0. So the inverse of infinite is 0. If this term is 0, then everything will be 0, because in multiplication, if one of the term is 0, then the whole multiplication is 0. It means if lambda will try to approach to infinity, ridge regression is 0. So both these cases are also verified with the help of this ridge regression equation. So this is the ridge regression equation which we can use in order to find the optimal value of weights. So here the weights will be controlled with the help of lambda. We study that lambda is the parameter which controls the amount of weight. So here in the ridge regression solution, we can see there is a lambda which will control the amount of weight and bias. So we can use this equation for reducing the weights and bias in order to avoid the overfitting. So we'll do it with the help of lambda. And similarly, we can also use this equation, because this equation is also used in order to penalize the weights with the help of lambda. So in this lecture, we learn about the ridge regression or L2 regularization. We understand that ridge regression is used in order to avoid overfitting. So in order to avoid overfitting, ridge regression use squared penalty on the vector. It has an important parameter known as lambda, which adjusts its value between 0 and infinity according to the value of the weights. So I hope you understood the concept of ridge regression. Thanks for listening, and I will see you in the next lecture.